Strip the universe of stars. Strip it of planets, dust, gas, light atoms, and heat. Remove every particle you know how to name. What remains should be nothing. That is the intuitive answer. It is also one of the deepest mistakes in modern physics. Because the closer science moved toward perfect emptiness, the more clearly it discovered that so-called empty space is not the absence of reality. It is the stage on which reality becomes possible, and more than that, it is part of the machinery itself. That is the tension we have to face from the start. The place we casually call nothing is not neutral. It is not inert. It is not a blank gap waiting for matter to arrive and make something happen. At the deepest level, we can currently describe what looks like emptiness is already structured, already occupied, already active in ways that shape every atom, every force, and every event you have ever experienced. The consequence is not small. If this is true, then our ordinary picture of the world is backward. An empty cup feels empty because it contains no water. An empty shelf feels empty because it holds no objects. An empty room feels empty because there is space to move through. Everyday intuition trains us to think of emptiness as subtraction. Take the contents away and what remains is just nothing. Clean, silent, featureless. That instinct is useful in daily life. It is also far too crude for the universe. Physics learned this the hard way. The more carefully matter was removed from a region, the less secure the old idea became. Air could be pumped out, dust could be filtered away, radiation could be reduced, temperature could be driven lower and lower, yet each time the image of a perfectly vacant region seemed close, a deeper layer appeared underneath it. Not a hidden object, not some last forgotten particle, something more unsettling. The space itself refused to become truly blank. This is where the real story begins, not with exotic particles, not with giant colliders, not even with the mathematics first. It begins with a correction to a very old human instinct. We think objects are the main actors, and empty space is the background. Modern physics suggests the opposite is closer to the truth. What we call particles may be secondary. What we call emptiness may be primary. And the cost of getting that wrong is enormous because it distorts how we picture matter, light, force, and even our own bodies. Pause on that for a moment. If empty space is not empty, then the darkness between stars is not a passive void. The gap inside atoms is not just unused room. The region around your hand, around your chair, around your lungs as you breathe is not a neutral absence. It is physically loaded. Something is there even when nothing visible is there. And whatever that something is, it is not optional. Remove it and the world does not merely change. It may stop being the kind of world in which atoms, chemistry, and stable matter can exist at all. That sounds abstract until you bring it back to scale. Consider a single atom. Most of its volume is often described loosely as empty space. That phrase is common because it helps communicate how tiny the nucleus is compared with the atom's full extent. But it also quietly misleads. Empty suggests dead volume. It suggests a hollow shell. The real situation is stranger. The interior of an atom is not a miniature room with nothing in it. It is a domain governed by fields, probabilities, interactions, and measurable effects that do not vanish just because solid little particles are not sitting there like pebbles in a box. The same mistake scales upward. Interstellar space looks empty because there are vast stretches with almost no matter. Intergalactic space looks emptier still. Darkness encourages the mind to imagine vacancy, but darkness is a visual verdict, not a physical one. The eye only reports what it can detect. It does not certify that nothing is present. This matters because one of the limits of human intuition is that we treat invisibility as absence. Physics does not have that luxury. It has to ask a harder question. Not what can I see there, but what must be there for the rest of reality to behave the way it does. That shift changes everything. By the end of this journey, the word empty will no longer mean what it meant when we began. It will no longer mean featureless non-existence. It will mean the quietest state available to a much deeper physical system. That is a very different claim. It does not say the vacuum is full in some poetic sense. It says the vacuum has properties, structure, and consequences. It says what appears calm may still be physically rich. And it says the most important layer of reality may be easiest to overlook precisely because it is always present. If that reversal interests you, leave a comment with the one idea about emptiness that feels hardest to let go of, because this topic only becomes more rewarding once that instinct starts to crack. There is another reason this matters. The issue is not merely philosophical. This is not a word game about how to define nothing. The vacuum in modern physics is not just a concept. It does things. It helps determine how forces spread. It affects how atoms behave. It enters the equations that predict measurable outcomes with astonishing precision. In other words, the question of emptiness does not sit at the decorative edge of science. It sits near the centre. And yet we have to move carefully. Some parts of this picture are established with extraordinary confidence. Other parts remain incomplete. Physics has very strong evidence that space is permeated by fields and that the vacuum is not a literal void. That much is on solid ground. But exactly how all of this connects to gravity, to cosmic expansion, and to the deepest architecture of reality is still unfinished. That limit matters. The honest version of this story is stronger than exaggeration, not weaker because the confirmed parts are already radical enough. So the map ahead is clear. First, we need to understand how the idea of emptiness began to fail. Then we need to see what replaced it. Not a new object inside the void, but a new picture of what the void ever was. Once that shift happens, matter stops looking like the obvious foundation of the world. An empty space starts to look like one of the most consequential physical entities in the universe. The old intuition will not survive that transition intact. It should not. Because the deepest surprise here is not that physics found activity where common sense expected silence. The deeper surprise is that the silence was never silence in the first place. It only sounded that way because we were listening for the wrong thing. For most of human history, the idea of a true void did not feel like an experimental question. It felt like a question about logic itself. Could there really be a region of reality containing absolutely nothing? No substance, no medium, no hidden filler, no support. To many early thinkers, the answer was no, and not because they lacked imagination. The answer seemed no, because a vacuum looked philosophically unstable. If nothing is there, what gives position meaning? What governs motion? What prevents the world from becoming unintelligible? Aristotle gave that instinct its most influential form. He argued that nature does not tolerate a vacuum. In later shorthand, the phrase became famous as nature abhors a vacuum. The important point was not the slogan, it was the structure of the argument. A completely empty region, in his view, would break the logic of motion. If no medium filled space, then nothing would regulate how bodies move through it. Motion would lose its natural order. The world would stop making sense in the way ancient physics expected it to. From a modern standpoint, Aristotle was wrong about the vacuum. But it is worth noticing what he was right about. He sensed that emptiness was not a trivial subtraction. He sensed that if a true void existed, it would force a deeper revision of physics. On that point, he was more perceptive than he is sometimes given credit for. The mistake was not taking the vacuum seriously. The mistake was concluding too early that it could not exist. That conclusion held enormous power. For centuries, European thought inherited a picture of the world in which space was never truly bare. If a region seemed empty, it was assumed to contain some thinner substance, air, vapor, ether, or something even more subtle. The idea of perfect nothingness was not just doubtful, it felt almost forbidden. Reality was imagined as a continuous, packed, filled through and through. Then experiment began to intrude. In the 17th century, Evangelista Torricelli performed one of the decisive acts in the history of physics. He filled a long glass tube with mercury, sealed one end, inverted it, and placed the open end in a dish of the same liquid. The mercury in the tube fell, but not all the way. It settled at a certain height, leaving a space at the top of the tube above the mercury column. That empty-looking region became the problem. What was in it? At first glance, the setup looked simple. In reality, it split a crack through 2,000 years of intuition. If the region above the mercury contained ordinary air, why had the mercury not fallen completely? If it contained no air, then perhaps a vacuum had been created. Torricelli proposed that the mercury column was being supported by the pressure of the atmosphere pushing on the dish below. The space above the mercury was not filled by some hidden upward force. It was, as far as he could tell, empty of air. That may sound modest now. At the time, it was explosive. The visual anchor matters here. Imagine the tube standing upright after inversion. Below a heavy silver column, Above it, a still pocket that seems to contain nothing at all. No cloud, no liquid, no visible material. A blank chamber suspended over metal. In that narrow gap, the old certainty began to fail. Still, resistance remained. One reason is obvious: instruments were limited. You could not directly inspect that region with the methods available. And this is one of the recurring limits in the whole story of emptiness. Humans do not encounter nothing directly. We infer it by ruling things out. That makes caution reasonable. A hidden vapour might still be there. A subtle substance might still escape detection. The eye could not settle the argument. So the debate moved from one experiment to another. Blaise Pascal pushed the matter further. If atmospheric pressure really supported the mercury column, then the height of that column should depend on how much atmosphere stands above the experiment. At higher altitude, there is less air overhead, so the pressure should be lower. That prediction is clean. It turns philosophy into a measurable gradient. Pascal's collaborators carried the instrument up a mountain and recorded the mercury height at different elevations. The result changed with altitude exactly as the pressure explanation required. The higher they went, the lower the column stood. This did not yet answer every metaphysical question about nothingness, but it did something more important for science. It showed that the behaviour of the apparatus was controlled by the weight of the atmosphere, not by some alleged impossibility of empty space. The world had shifted. Then came an even more dramatic demonstration. Otto von Guericke built an air pump and used it to evacuate large metal hemispheres pressed together. Once the air inside had been removed, teams of horses pulling from opposite sides could not separate them. Only when air was allowed back in did the hemispheres come apart. The lesson was not that the vacuum had become sticky. The lesson was that the surrounding atmosphere was pushing with enormous force. Again, the image does the work. Two hollow halves locked together, horses straining, leather harnesses taut, nothing visible between the metal shells, and yet something outside equally invisible pressing so hard that brute force cannot win. The scene corrected more than one intuition at once. It showed that air has weight. It showed that pressure is not an abstraction. And it showed that a region from which air has been removed behaves differently in a law-governed way. By the late 17th century, the existence of at least partial vacuum was difficult to deny. Robert Boyle improved pumping techniques and used evacuated vessels to study how phenomena changed when air was removed. One famous demonstration involved sound. Put a ringing object inside a chamber. Pump the air out. The object can still be seen, but its sound fades and disappears. That distinction mattered. Sound needs matter to travel through. Remove the medium, and the vibration has no ordinary path. But the story did not end with therefore the chamber is truly empty. Quite the opposite. This is the crucial correction. Early vacuum experiments did not reveal pure nothing. They revealed that one particular thing air was absent. That is not the same claim. It sounds similar, but the difference is enormous. Once that distinction is clear, the entire history that follows becomes easier to understand. Scientific progress here did not move from full space to empty space. It moved from space must always be filled with familiar substance to removing familiar substance does not settle what space itself contains. That is the hinge. A vacuum chamber without air still allows light through. It still permits forces to act across it. Magnets influence objects across gaps. Electrified bodies affect one another without contact. Gravity reaches through regions where no obvious medium can be seen. So even after the atmosphere was demoted from invisible support to measurable gas, a harder question remained behind it. What exactly occupies the region between objects when no ordinary matter is there? That question will force physics into a deeper revision than the 17th century could yet provide. The old fullness has been weakened but not replaced. The air is gone, the puzzle is not. And once that puzzle becomes unavoidable, the target is no longer the contents of space alone. The target becomes the meaning of space itself. Once air was removed from the problem, a more subtle difficulty came into view. A chamber might be emptied of gas and still refuse to behave like pure nothing. Light crossed it. Gravity ignored its apparent blankness. Magnets acted through it. Electric charges influenced one another across it, so the vacuum question changed shape. The issue was no longer whether space could be empty of ordinary matter. The issue became more unsettling. If no visible substance connects objects, how do forces pass from one place to another at all? For a long time, physics tolerated a strange answer. It described forces accurately without explaining their carrier. Newton's law of gravitation could predict planetary motion with extraordinary success. Two masses attracted each other according to distance and mass. The mathematics worked, yet the mechanism remained obscure. How does the sun affect Earth across millions of miles? How does one body reach across what appears to be emptiness and pull on another body it never touches? Newton himself did not present that mystery as solved. He gave physics a law of astonishing power, but not a satisfying physical picture of what travelled between the bodies. This matters because it reveals a limit in scientific understanding that appears again and again. A theory can predict correctly before it explains comfortably. Nature will often let you calculate long before it lets you feel that you understand. By the early 19th century, electricity and magnetism made the problem impossible to ignore. These forces were intimate, local, repeatable, and experimentally rich. A magnet pulls iron without contact. A charged rod moves bits of paper without contact. Something seems to occupy the intervening region. But what? If the region is truly nothing, then action at a distance becomes an increasingly awkward phrase. It is a name for the problem, not a solution to it. Michael Faraday changed the picture. Faraday was not famous for abstract mathematical formalism. He was famous for physical intuition of a very rare kind. He had a way of treating invisible processes, as if they had shape, direction, and tension before the equations were fully written down. Instead of imagining one object mysteriously tugging on another through empty space, Faraday proposed that the sun's space around the object itself is altered. A magnet does not merely wait until iron appears and then reach for it. It creates a magnetic field in the surrounding region. An electric charge creates an electric field around itself. Another object entering that region responds to the field where it is. That sounds like a small change in wording. It is not. The old picture says object acts on object across emptiness. The new picture says object creates a condition in space and another object responds to that local condition. The intermediary is no longer a mystery hidden in a gap. The intermediary is the field filling the gap. Faraday's most memorable visual anchor made this almost impossible to unsee. Scatter iron filings around a magnet and they do not lie randomly. They arrange themselves into graceful curves arching from pole to pole. Those curves are not the field itself, but they reveal its structure. The filings align with what Faraday called lines of force. Suddenly, the empty region around the magnet no longer looks blank. It looks organized, directed, tensioned. Space has acquired physical character. This corrected a major intuition. Before this shift, it was easy to think of space as a passive container. After Faraday, that picture began to collapse. Space could host a field with a strength and direction at every point. Even if no iron filing, no charge, and no detector was placed there, the field could still exist. The region between objects was not merely where nothing happened. It was a physically meaningful part of the story. James Clerk Maxwell gave this intuition mathematical force in the 1860s. He wrote the equations that unified electricity and magnetism into a single framework. These equations did far more than tidy up known effects. They implied that changing electric fields generate magnetic fields, and changing magnetic fields generate electric fields. Once that structure is in place, a remarkable possibility appears. Disturbance can sustain itself. Electric and magnetic changes can propagate together as a wave through space. When Maxwell calculated the speed of that wave using known electrical and magnetic constants, the result matched the measured speed of light. This was one of the great recognitions in physics. Light was not a separate phenomenon after all. Light was an electromagnetic wave. Visible light, radio waves, infrared, ultraviolet, all of them belonged to the same family. The consequence for the idea of emptiness was immediate and profound. If a light crosses apparently empty spaces as an electromagnetic wave, then the electromagnetic field must not be absent there. It must already be present. The wave is not carrying emptiness with it. It's a disturbance of something that fills the region in advance. That single step quietly overturns an old worldview. Consider a star helm seen on a clear night. Its light may have travelled for years, centuries, or far longer through regions with barely any atoms. By ordinary standards, that journey crosses near perfect emptiness. Yet if light is an electromagnetic wave, then the route is not empty in the strict sense at all. It is occupied everywhere by the electromagnetic field. The darkness between star and eye is not a literal void. It is a medium of physical possibility, even if not a material medium in the old mechanical sense. That distinction matters. Physics had once imagined that waves required a substance like water or air. Sound does. Water waves do, rope waves do. So many 19th century scientists assumed light must also need a material carrier, a luminiferous ether. But the deeper lesson of Maxwell's theory is subtler. Light needs a field, not a classical substance. The electromagnetic field is real, but it is not a gas, not a liquid, not a hidden wind in space. This is a point where intuition easily overshoots. One should not picture the field as invisible smoke filling the cosmos. A field is not ordinary matter spread thin. It is a different kind of physical entity. That is an important limit of intuition. Everyday imagination is built on objects and materials. Fields force the mind into a less comfortable category. They have measurable effects. They carry energy. They can vary from point to point. But they are not chunks of substance in the familiar sense. Physics here becomes harder not because it is vague, but because ordinary visual habits are too coarse. By the end of the 19th century, the revision was already severe. Empty space could no longer mean a region devoid of physical content. Even if matter had been removed, the electromagnetic field remained. And once one field is admitted, the old vacuum is gone in a stronger sense than the 17th century had imagined. A vacuum is not just airless. It is a region in which at least some fields are still present. That alone would be enough to change the meaning of emptiness, but the revision is not finished yet, because classical fields, rich as they are, still allow one last refuge for common sense. They can in principle rest quietly at zero. They can be present as part of reality, and yet remain perfectly still in some region. The next revolution will take even that away. Once quantum theory enters the story, the calm field itself begins to tremble. By the start of the 20th century, physics had already given up one version of emptiness. Space was no longer a blank container. It carried fields. The electromagnetic field filled the regions through which light travelled. Gravity, too, seemed less like a mysterious pull across nothing and more like a property attached to the structure of the world itself. But there was still a refuge for the older intuition. Even if fields existed everywhere, perhaps they could at least become perfectly quiet. Perhaps the deepest vacuum was simply a place where all fields sat motionless at zero. That hope does not survive quantum theory. Before we get there, it helps to see the last classical picture clearly. In classical physics, a field can be present as part of reality without showing any local activity. No waves, no excitations, no energy flowing through. Just zero value in a region. A perfectly calm sea with no ripples. This is the most refined classical version of emptiness. Not the absence of the field itself, but the absence of any disturbance in it. The stage remains, but the stage is silent. Then 20th century physics began to break the silence. Einstein's general theory of relativity had already deepened the status of gravity. In Newton's framework, gravity was a force acting across distance. In Einstein's picture, what we call gravity reflects the geometry of space-time itself. Matter and energy is shaped that geometry, and free-falling bodies move accordingly. This is not yet quantum theory, but it matters for the story because it pushes physics further away from the old image of space as passive emptiness. Space and time are not merely where events occur. Their structure participates in the events. Still, relativity alone does not force vacuum restlessness. For that, the decisive pressure came from quantum mechanics. The path opened with a crisis over heat and light. Classical physics predicted that a hot object should pour more and more energy into higher frequencies without limit. That result was obviously wrong. Real hot objects glow, but they do not emit infinite energy. Max Planck found a way to repair the mathematics by proposing that energy is exchanged in discrete packets. He did not begin by trying to overthrow reality. He began by trying to save a calculation, but the fix changed everything. A little later, Einstein pushed the rupture further. Light itself behaved in some experiments as if it came in packets later called photons. This explained the photoelectric effect where light can eject electrons from a material only if its frequency is high enough. Brightness alone is not enough. That result was a direct blow to any comfortable picture of light as only a smooth classical wave. The world at small scales was not merely continuous, it came granular quantized, resistant to the old intuition. Then the full quantum framework emerged. Heisenberg, Schrödinger, Born-Dirac and others built a theory that worked with astonishing success. But what matters for the vacuum story is not only that quantum mechanics predicts probabilities, it is that quantum mechanics places hard limits on what it means for a system to be perfectly still. The most famous expression of that limit is the uncertainty principle. Usually it is introduced through position and momentum. The more precisely one is fixed, the less sharply the other can be fixed at the same time. That phrasing can make it sound like a defect in measurement. It is deeper than that. The uncertainty is not mainly about clumsy instruments. It is built into the structure of quantum states themselves. For fields, the consequence is severe. A quantum field has a value, and it also has a corresponding rate of change or momentum-like quantity. In classical reasoning, both could be exactly zero in a truly calm vacuum. In quantum reasoning, demanding exact stillness becomes impossible. If the field value were pinned down with perfect sharpness everywhere, the conjugate quantity would become radically uncertain. If the rate of change were fixed with perfect sharpness, the field value would blur. The result is not a loophole, it is a prohibition. The field cannot sit in an exact, perfectly silent zero state in the classical sense. This is where the ordinary imagination starts to fail, and it helps to use a more tangible image. Think of a simple mass on a spring. In classical mechanics, you can stop it exactly at equilibrium. No motion, no stored kinetic energy, no oscillation, just rest. In quantum mechanics, the analogous system does not allow that total stillness. Even in its lowest possible energy state, it retains a residual jitter. Not because the room is vibrating, not because heat is sneaking in, not because the apparatus is poorly built. The jitter is intrinsic. The lowest state is not motionless in the classical sense. That residual minimum is called zero-point energy. Now scale that idea up carefully. A quantum field can be thought of in one useful mathematical sense as an enormous collection of oscillatory modes. Each mode behaves like a quantum oscillator, and if each oscillator keeps a minimum irreducible amount of activity, then the field as a whole cannot be perfectly dead. Even at absolute zero, even with no real particles present, even after every ordinary source of disturbance has been removed, the field retains fluctuations. That is the crucial correction. The vacuum is not empty space plus calm fields. It is the lowest energy state of the fields, and the lowest energy state is still active. Not dramatically active in the everyday sense. Not boiling with visible particles all the time, but not silent either. The vacuum becomes a state of irreducible restlessness. This is where language becomes dangerous. Words like fluctuation can make the process sound like random shaking in a classical medium. That is only partly helpful. Quantum fluctuations are not little hidden billiard balls bouncing around in a dark box. They are not thermal noise. They are not evidence that the system failed to settle down completely. They are what settling down completely means in a quantum world. That distinction matters because it blocks a common misunderstanding. One might think that if the vacuum fluctuates, then perhaps there are always ordinary particles lurking there unnoticed. That is too crude. The established claim is more careful. The vacuum is the ground state of the quantum fields. That state contains no real particles in the ordinary detector sense, yet it is not featureless. The fields retain structure and dynamical possibility even in that ground state. Another limit of intuition appears here. Human experience trains us to associate lowest energy with passivity. A cooled object quiets down. A pendulum comes to rest. A ringing glass goes silent. In quantum theory, the analogy breaks at the deepest level. Lowering energy does not mean reaching a perfectly inert floor. It means reaching the minimum allowed by the rules, and the rules do not permit total stillness. That reversal transforms the meaning of the vacuum more radically than anything we have met so far. The 17th century taught that a vacuum could be empty of air. The 19th century taught that fields still remain. The quantum 20th century adds something even sharper. Those fields do not merely remain as a passive backdrop, they continue to fluctuate in their lowest state. The void is not merely occupied, it is alive with minimum activity. And this is no longer just a conceptual preference. Once that claim is made, physics owes us consequences. If vacuum fluctuations are real, they should leave fingerprints. They should shift energies, alter forces, or change measurable behavior somewhere in the world. Otherwise, the idea risks becoming decorative language around the equations. The remarkable fact is that those fingerprints do appear, so the next step is unavoidable. We have to leave the level of principle and go to the level of experiment. Because the boldest part of the story is not that quantum theory permits a restless vacuum. The boldest part is that the vacuum's restlessness can be measured. A restless vacuum would remain a beautiful idea and nothing more if physics could not connect it to the behaviour of matter. The claim is too strong to leave hanging in abstraction. If empty space is this ground state of quantum fields, and if those fields cannot be perfectly still, then the next question is unavoidable. What exactly is doing the fluctuating? What is the thing that remains when all ordinary particles are gone? The answer marks one of the deepest reversals in modern science. The primary ingredients of the universe are not particles, they are fields, and what we call particles are specific localized excitations of those fields. This is the point where the old mental picture starts to crack for good. The intuitive image of matter is almost always object-based. Electrons are imagined as tiny specks, quarks as even tinier specks, photons as little pellets of light. The scale changes, the imagery does not. We keep shrinking ordinary objects in the mind and hope reality will follow. That instinct is understandable. It is also misleading. Quantum field theory does not describe the world as a box of miniature beads moving around inside empty space. It describes a world in which fields are everywhere all the time, and particles are the temporary ways those fields become excite. A good first anchor is a stretched surface of water. Drop energy into it and a ripple forms. The ripple has a location. It moves. It carries energy and momentum. You can track it. You can measure its speed. But if you ask what the ripple is made of, the answer is not ripple stuff. The answer is water. The ripple is a behavior of the underlying medium, not an independent ingredient added on top. That image helps, but only to a point. A quantum field is not a material liquid filling the universe. It has no visible surface, no ordinary substance, no little molecules underneath it. The analogy is useful because it breaks the grip of the object picture. A particle is not best understood as a tiny self-contained thing. It is best understood as a field doing something specific. That correction matters enormously. Take the electron. In modern theory, there is an electron field spread throughout all of space, not just near atoms, not just where electrons happen to be detected, everywhere. When this field is excited in the right quantized way, an electron appears. The particle is the excitation. The field is the underlying reality. The same logic applies across the board. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. In each case, the field is fundamental. The particle is a localized pattern in that field. Once that shift is made, several old puzzles become less mysterious. One is particle identities. Every electron in the universe appears to be exactly identical to every other electron. Same mass, same charge, same spin, not approximately the same, and exactly the same as far as measurement can tell. In the old object-based picture that is surprisingly hard to make intuitive, if electrons were independent little items, why would they not vary at least slightly? Why no manufacturing tolerance? Why no tiny difference from one to another? In the field of picture, the answer becomes natural. They are identical because they are not independently manufactured objects. They are excitations of one and the same field. Just as identical notes played on the same instrument share the same structure, identical electron excitations share the same properties because those properties come from the field itself. The sameness is not a coincidence, it is built in. Another puzzle is the creation and destruction of particles. In older ways of thinking, matter seems like something that should persist as countable little units. Rearranged perhaps, broken apart perhaps, but not truly created from scratch or annihilated into something else. Yet high-energy physics shows that particles can be created and destroyed routinely. A photon with enough energy can produce an electron and a positron under the right conditions. An electron and a positron can annihilate and yield photons. In the field picture, this is no longer bizarre. Energy is being transferred between fields. The electromagnetic field loses energy in one process, and the electron field gains enough to support new excitations. In the reverse process, excitations in the electron field disappear, and their energy reappears as excitations of the electromagnetic field. No magical appearance of matter from nothing, no tiny object turning into another object by a narrative trick, just fields exchanging energy and changing which excitations are present. Historically, this picture did not arrive all at once. One of the key turning points came from Paul Dirac in the late 1920s. Dirac wanted a quantum equation for the electron that respected special relativity. He succeeded, and the equation was brilliant. It naturally accounted for electron spin and predicted phenomena that earlier quantum mechanics had not made feel inevitable. But it also produced something profoundly strange. Negative energy solutions appeared. That was not a harmless mathematical oddity. If such states were physically allowed in a naive way, electrons should tumble endlessly down into lower and lower energies. Ordinary matter would become unstable. The world would not look like the world. Dirac's initial way of dealing with this difficulty involved an infinite sea of filled negative energy electron states. It was ingenious, and it led to a spectacular prediction the positron, the electron's antimatter partner, later discovered experimentally, but the deeper resolution was cleaner than the sea picture. The true advance came when physicists learned to quantize the fields themselves. Then the electron and positron could be understood as different excitations of the same underlying field. The awkward infinity of invisible occupied states was no longer needed as the main picture. What remained was more elegant and more powerful. Fields are the basic entities. Particles emerge from them. This is also where a limit of intuition should be stated plainly. When physicists say a field fills all of space, that does not mean every point is crammed with ordinary detectable stuff. It means the field is defined everywhere. It is available everywhere. It can be excited anywhere. Confusing that with hidden classical material leads the mind in the wrong direction. A field is not a gas smeared thinly across the cosmos. It is a different category of physical reality, known through its effects, its equations, and the excitations it supports. By now, the vacuum itself starts to look different. If all these fields extend everywhere, then a vacuum cannot mean a place where the fields are absent. Their absence would mean the absence of the very framework from which particles arise. A vacuum means something more precise and more subtle. It means the fields are present but unexcited in the sense of having no real particles. Yet because they are quantum fields, even that unexcited condition is not perfectly still. The ground state keeps its residual activity. So the conceptual ladder is now in place. Empty space is not empty because fields are there. Fields are fundamental because particles are their excitations. And the vacuum is not dead because the fields remain quantum even in their lowest state. The next step is to make this less philosophical and more physical. If fields are primary, then their interaction should not merely give us a new language for matter. They should let us calculate the world with astonishing precision. They should explain how forces are transmitted, how particles influence one another, and why the vacuum itself leaves measurable traces behind. That is where the theory stops sounding like a reinterpretation and starts proving its power. Once fields become the main actors, physics has to do more than offer a fresh way of speaking. It has to earn the right to replace the older particle picture by calculating real phenomena more accurately than any rival framework. That is exactly what happened. The field view did not survive because it was philosophically elegant. It survived because it became one of the most successful predictive structures ever built by the human mind. And the place where that success first reached overwhelming force was the quantum theory of light and matter. This theory is called quantum electrodynamics, often shortened to QED. The name can sound forbidding, so it helps to define it cleanly. QED is the quantum field theory of the electromagnetic interaction. In plain terms, it describes how electrically charged fields and the electromagnetic field influence one another. It tells us how electrons interact with light, how charges repel or attract, and how the vacuum itself enters those processes. That is the formal definition. The physical picture is easier to hold if you imagine reality not as isolated objects colliding in a void, but as fields constantly exchanging quantized disturbances. An electron does not merely sit in space and then suddenly feel another electron from afar. In the quantum field picture, the interaction is mediated through the electromagnetic field. The language of calculation often describes this as an exchange of photons. Sometimes those photons are real and detectable as in ordinary light. Sometimes they are virtual, meaning they appear inside the mathematics of an interaction without emerging as free particles in a detector. The term virtual should be handled carefully. It does not mean imaginary in the everyday sense. It means intermediate, fleeting, internal to the process, rather than directly observable as an outgoing particle. This is one of those places where intuition needs correction. When people hear that two electrons repel each other, by exchanging photons, they may picture one tiny bead throwing another tiny bead back and forth across space. That image is too crude. The better picture is that the electron field and the electromagnetic field are coupled. Their allowed quantum interactions can be represented mathematically as exchange processes, and those exchanges carry momentum. What we call force is the measurable effect of that field-mediated transfer. Richard Feynman gave physicists a visual grammar for these interactions. His diagrams are deceptively simple. A straight line may represent an electron. A wavy line may represent a photon. Where the lines meet, an interaction occurs. Draw enough of these combinations and you can systematically compute the probability of scattering emission, absorption, or more subtle corrections. The drawings look almost childlike at first, yet they encode some of the most precise predictions ever made. The visual anchor here is worth keeping. Imagine a black page crossed by clean white lines. One straight path enters, another leaves. A wavering line bridges them. At a glance, it looks like a sketch. Underneath it stands for a full mathematical contribution to a physical process. The charm of Feynman diagrams is not that they simplify the theory into a cartoon. It is that they let the structure of a process become visible without hiding the complexity. And the complexity is real. A single electron is not truly single in the old classical sense. In quantum field theory, it is inseparable from the fields with which it interacts. As it moves, it can emit and reabsorb virtual photons. Those virtual photons can briefly contribute to further processes. In the mathematics, what first looked like a lone particle becomes surrounded by a haze of possible field activity. This is not a decorative flourish. It changes measurable quantities. The electron you observe is not a bare mathematical point stripped of all interactions. It is a dressed excitation shaped by the vacuum and by its coupling to other fields. This was not easy to tame. Early quantum field theory ran into terrifying infinities. Calculations of self-energy and interaction strength often exploded. Instead of finite measurable answers, the equations produced divergent terms that seemed to threaten the entire program. For a time, it looked as if the theory might be elegant but broken. This is another useful reminder of science's limits. A deep idea does not arrive fully polished. Sometimes it arrives with mathematics that appears pathological, and only later do better tools reveal how to interpret it. The breakthrough came with renormalization. The word can sound technical, but the central idea is surprisingly concrete. The raw parameters appearing in the earliest version of the equations are not identical to the values we measure directly in the lab. Observable mass and observable charge already include the influence of field interactions. Renormalization reorganizes the theory so that the infinities are absorbed into unobservable bare quantities, leaving finite predictions for measured ones. That may sound like a trick the first time you hear it. Its credibility comes from what follows the numbers work, and they work with astonishing precision. This is where quantum field theory stops being merely persuasive and becomes unavoidable. QED predicts measurable effects to an accuracy unmatched elsewhere in science. Scattering experiments, atomic shifts, and magnetic properties all line up with calculations to extraordinary precision. The agreement is not rough. It is not qualitative. It is numerical in a way that almost strains belief. A theory describing fields' virtual processes and vacuum contributions turns out to match experiment to many decimal places. That precision is itself a correction of intuition. Common sense often assumes that the most successful theories are the most visually simple. But the world does not owe us visual simplicity. The object-based picture is easier to imagine. The field-based picture is harder to imagine and vastly more successful. Reality is under no obligation to resemble the metaphors that feel comfortable in the human skull. QED was only the beginning. The same field logic expanded outward. The weak nuclear interaction responsible for certain forms of radioactive decay was incorporated into a larger framework together with electromagnetism. This electroweak theory introduced additional fields whose excitations are the heavy force carriers known as the W and Z bosons. Later, the strong nuclear interaction which binds quarks inside protons and neutrons was described through quantum chromodynamics. There, the relevant fields include quark fields and gluon fields with rules more complicated than electromagnetism because the carriers of the force also interact among themselves. Put together, these theories form the standard model of particle physics. It is not complete in every sense. It does not yet incorporate gravity in a quantum framework. It leaves major cosmological puzzles unresolved. But within its domain, it is spectacularly successful. And its core message is consistent throughout. Every known fundamental particle corresponds to an excitation of a field. Matter fields, force-carrying fields, the Higgs field, different roles, same underlying logic. That means the room around you right now is not merely inhabited by particles that happen to be nearby. It is permeated by all the relevant fields, whether or not any real particles are present at a given point. The electron field is here, the electromagnetic field is here, the quark fields are here, the Higgs field is here, their excitations may be absent locally, the fields are not. This matters because it sharpens the meaning of the vacuum. A vacuum is not a place where the framework of reality has been erased. It is a place where the fields sit in their ground state with no real particles riding above that baseline. But because quantum field theory allows interactions, couplings, and residual fluctuations, that baseline is already physically rich. So now the stage is set for a more decisive move. We no longer just know that the vacuum contains fields. We now know that those fields interact with exquisite measurable consequences. The next question is therefore unavoidable. If the fields remain present in the vacuum, and if quantum theory forbids perfect stillness, can the vacuum itself push, shift, or alter the world in ways we can test directly? The answer is yes. And once those tests appear, empty space stops being a philosophical problem and becomes an experimental fact. By this point, the vacuum has already lost its old meaning. It is no longer a blank absence. It is no longer merely a region where air has been removed. It is no longer even just a place where fields exist quietly in the background. In quantum field theory, the vacuum is defined much more precisely. It is the lowest energy state of all the fields present in nature. That definition sounds calm, it sounds final, it sounds as if we have at last reached the floor. But the crucial twist is this: the floor is not zero in the way classical intuition expects. To see why it helps to return to the simplest useful model. A quantum harmonic oscillator is the quantum version of something like a mass on a spring. Classically, the lowest energy state is easy to picture. The mass sits exactly at rest in the middle. No motion, no kinetic energy, no oscillation. But quantum mechanics refuses that perfect stillness. The lowest energy state still carries a minimum irreducible amount of energy. The oscillator jitters even when it has been cooled as far as the laws of nature allow. That residual minimum is not a flaw in the setup. It is not due to heat leaking in from the room. It is not due to hidden imperfections in the apparatus. It is the genuine ground state. And that detail is decisive because quantum fields can be decomposed into modes that behave mathematically like vast collections of oscillators. Each mode has its own minimum energy. So when we talk about the vacuum of a field, we are not talking about a dead featureless zero. We are talking about a structured ground state in which every allowed mode retains its irreducible quantum residue. This is the point where the word vacuum starts to mislead almost by habit. In ordinary language, vacuum suggests an empty chamber. In quantum theory, vacuum means the state with no real particles present. Those are not the same idea. A room can be evacuated of air and still contain fields. A field can contain no real particles and still possess zero-point activity. So when physicists say the vacuum fluctuates, they are not saying the chamber secretly contains ordinary dust-like objects flickering in and out of view. They are saying the lowest energy state of the fields is not classically silent. That difference needs to be kept sharp because the imagination tends to overshoot. Popular retellings often slide too quickly from vacuum fluctuations to particles popping in and out of existence everywhere. There is a kernel of truth in that language, but it can become misleading if treated too literally. The most secure statement is more disciplined. The vacuum state contains non-zero correlations and non-zero zero-point structure. Under certain circumstances, those features can be described in ways that resemble transient particle-like processes. But the bedrock fact is not a cartoon of tiny objects flashing in and out. The bedrock fact is that the ground state of the fields is physically non-trivial. That may sound technical, but its consequences are not small. A classical vacuum would be passive, it would contribute nothing except empty separation. A quantum vacuum is different. Because the fields retain irreducible fluctuations, the vacuum has measurable influence. It can alter energy levels, it can modify interactions, it can produce forces under the right conditions. The background is no longer just a background, it participates. There is also a scale translation worth pausing over here. Human senses evolved for warm, slow, dense environments. We are good at tracking macroscopic objects. We are terrible at intuiting ground states of quantized fields. This matters because one of the great limits of direct intuition is that stillness at our scale does not mean stillness at all scales. A glass of water can look flat while its molecules are in furious motion. A metal beam can look rigid while its atoms vibrate. Quantum fields take that lesson deeper still. Even when every classical sign of activity has been suppressed, the lowest available state retains motion-like structure that no cooling procedure can erase. Now bring that back to empty space itself. Imagine the best vacuum chamber humanity can build. Air removed, stray radiation reduced, temperature driven toward absolute zero. Classical thinking says the region should approach nothing. Quantum field theory says something subtler. The chamber approaches the vacuum state, yes, but the vacuum state is not a literal void. The electromagnetic field remains there in its ground state. So do the electron field, the quark fields, the neutrino fields, and the Higgs field. No real particles need be present. The fields remain. And because they are quantum fields, they do not settle into a perfectly dead baseline. This correction is profound because it changes what lowest possible activity means. The quietest state the universe permits is not empty in the classical sense. It is a sea level, not a dry floor. Calm compared with storms, yes, but not nothing. That image of sea level helps for another reason. Waves can rise above it, and those waves are like particles, but even when no waves rise high enough to count as real particles, the level itself is present. It structures what can happen. It defines the baseline from which excitations emerge, and because quantum theory forbids perfectly sharp stillness, even the baseline is textured. At this stage, an honest limit should be stated. The language of field value and fluctuation is mathematically precise inside the theory, but not always easy to translate into ordinary pictures without distortion. If one pushes the imagery too hard, it becomes false. The vacuum is not a hidden classical fluid. It is not a storage room full of miniature latent objects. It is a quantum state. That is one reason the topic often feels slippery. The most accurate description is more abstract than intuition likes, yet the abstract description makes predictions that experiments repeatedly confirm. And that is the key point. We are no longer talking about a philosophical preference for richer language. We are talking about the actual baseline state required by the most successful theory of matter and light ever built. If the vacuum were truly empty in the old sense, many observed effects would come out wrong. The world would not behave as measured. The apparent emptiness of space would fail to do what real empty space actually does. So the next step is no longer optional. Once the vacuum has been defined as the lowest energy state of the fields, and once that state has been understood as physically restless rather than dead, the theory owes us experimental fingerprints. Not vague ones, clear ones, measurable ones. The vacuum must do work in the world somewhere, or the idea remains too easy to misread as formal language wrapped around nothing. The remarkable thing is that those fingerprints exist, and they are not hidden at the edge of physics. They appear in some of the most elegant and important measurements ever made. Empty space under the right circumstances can push metal surfaces, shift atomic energy levels, and help determine how light is emitted in the first place. That is where the quiet ground state stops sounding theoretical and starts becoming impossible to ignore. If the quantum vacuum were only a mathematical subtlety, it would remain easy to dismiss. The language is abstract enough that common sense can always try to retreat. Perhaps fluctuations are just bookkeeping. Perhaps the fields are just a formal trick. Perhaps empty space still behaves like nothing in every experimentally serious sense. That line of escape fails the moment the vacuum starts leaving fingerprints on matter. And it does, not once, not vaguely, repeatedly. The first major example is the Casimir effect. The basic setup is simple enough to picture. Take two uncharged conducting surfaces and place them extremely close together in a vacuum. No applied voltage, no conventional attraction from opposite charges, no obvious mechanical linkage. Classically, one might expect nothing remarkable to happen. The plates are neutral, the gap is empty, so the region between them should just sit there. It does not. Quantum electrodynamics predicts that the plates should feel a force pulling them together. The reason is subtle and beautiful. The electromagnetic field fluctuates even in the vacuum, but the conducting boundaries imposed by the plates restrict which field modes can exist in the narrow gap between them. Outside the plates, the field has a wider range of allowed fluctuations. Inside the gap, some of those modes are excluded. The result is an imbalance. The vacuum state between the plates is not identical to the vacuum state outside them. That difference in allowed zero-point structure translates into a measurable force. This is one of the best places to correct intuition carefully. The plates are not attracted because the vacuum is full of hidden air pressing on them, nor because the plates somehow acquire ordinary opposite charges. The effect comes from the way the quantum ground state of the electromagnetic field is altered by geometry. Change the boundaries and you change the vacuum modes. Change the modes and you change the energy. The force follows from that difference. The visual anchor is striking. Two metal surfaces facing each other across a gap so tiny that the separation is measured in fractions of a human hair. Nothing visible between them. No wire, no spark, no obvious cause, and yet the plates drift inward because empty space under constraint is not physically neutral. The Casimir effect was predicted in the 1940s and measured much later with increasing precision as instrumentation improved. That timing matters because it reveals a limit of observation. The effect is small. Measuring it demands careful control over geometry, contamination, thermal influences, and electrostatic noise. So the delay between theory and clean experiment should not be mistaken for weakness. It reflects the fact that vacuum forces are subtle at human scales. Nature is not obliged to make foundational effects easy to detect with coarse tools. The second major fingerprint comes from atomic structure. This is the Lamb shift. In the simplest early relativistic description, uncertain energy levels in hydrogen were expected to be exactly the same. But precision measurement showed a slight difference where the naive theory predicted degeneracy. The discrepancy was tiny but unmistakable. And tiny discrepancies matter in physics because they often indicate that the apparent background is doing more than the first model allowed. What shifts the levels? Vacuum fluctuations of the electromagnetic field. The electron in the atom is not orbiting through a classically empty region. It is embedded in a fluctuating quantum environment. Those fluctuations slightly perturb the electron's behavior, and the size of the effect depends on the structure of the orbital state. Different states feel the vacuum differently. The result is a measurable shift in their energies. This is a powerful correction of intuition. We tend to imagine the atom as a small self-contained object whose internal behavior depends only on its own parts: nucleus, electron, electrostatic attraction. The Lamb shift says that picture is incomplete. The atom is not sealed off from the vacuum. Even when no real photons are present, the quantum ground state of the electromagnetic field modifies what the atom can be. That brings us to a third effect, one so common that it hides in plain sight: spontaneous emission. An excited atom can emit a photon and drop to a lower energy state without any obvious external trigger. That process is so familiar that it rarely feels strange. But from a classical perspective, it is deeply non-trivial. Why should an atom radiate if nothing perturbs it? Why does it not simply remain in the excited state indefinitely unless nudged? Quantum field theory gives the answer. The vacuum itself provides the perturbation. The excited atom is coupled to the fluctuating electromagnetic field even when no real light is present. Those vacuum fluctuations open the channel for emission. In that sense, spontaneous emission is not causeless. It is spontaneous relative to ordinary classical triggers, but not relative to the quantum vacuum. This matters more than it first appears. Spontaneous emission is not a marginal oddity. It helps determine how atoms radiate, how lasers are understood, how spectroscopy works, and how light from excited matter is produced throughout nature. A supposedly empty background is participating in one of the central mechanisms by which the visible world shines. Notice the progression here. The Casimir effect shows that vacuum structure can generate force. The Lamb shift shows that vacuum fluctuations can alter atomic energy levels. Spontaneous emission shows that vacuum coupling can influence radiative transitions themselves. In each case, the message is the same. Empty space is not an inert stage. it changes outcomes. There is also a broader lesson about scientific realism. Physicists do not accept vacuum fluctuations because the phrase sounds profound. They accept them because eliminating them breaks successful predictions. This is a different standard from metaphor. If you remove vacuum contributions from the calculation, the numbers stop matching what laboratories observe. The theory loses contact with the world. That is why the vacuum's activity is not optional, it is demanded by evidence. Still, honesty requires one more distinction. These effects do not mean the vacuum has been fully understood in every respect. They prove that the vacuum is physically consequential. They do not solve every interpretive debate about how best to visualize what is happening. In some formulations, the effects are described in terms of fluctuating fields. In others, emphasis may fall on boundary conditions, state changes, or response functions. The measurable reality is secure even where the preferred language differs. That is another limit worth remembering. Physics often knows more precisely how to calculate than how to narrate, but the conclusion is already firm enough. A force with no classical cause, atomic levels shifted by the background itself. Light emitted because the ground state of the field is not truly silent. These are not decorative complications. They are direct evidence that the vacuum is an active participant in the behaviour of matter, and once that much is granted, one more step becomes irresistible. If the vacuum can alter atoms and push plates, then it may also modify the properties of particles themselves. Not just the behaviour of systems placed in space, but the measurable identity of the excitations we call particles. That is where the precision becomes almost unbelievable. By the time the vacuum can push metal plates and shift atomic energy levels, the old image of empty space is already in ruins. But there is an even sharper test. Instead of asking whether the vacuum changes what systems do, ask whether it changes what particles are. Not in a poetic sense, not in a loose philosophical sense, in a measurable, numerical, brutally precise sense. If a particle is really an excitation of a quantum field embedded in a restless vacuum, then its observable properties should carry the imprint of that environment. And one of the cleanest places to look is the electron. The electron behaves like a tiny magnet. This magnetic behaviour is tied to its spin, a fundamental quantum property that has no true classical analogue, even if it is often described with spinning imagery. The key measurable quantity here is called the magnetic moment. Dirac's relativistic quantum theory gave an elegant first prediction for it. In the simplest approximation, the relevant factor comes out to exactly 2. That result was already impressive. It emerged naturally from the structure of the theory rather than being inserted by hand. But nature was more precise than the first theory. When experiments measured the electron's magnetic behaviour carefully, they found that the value was not exactly 2. It was slightly larger. The deviation is tiny, so tiny that at first glance it could seem almost irrelevant. But in precision physics, tiny is where the deepest truths often hide. A minute mismatch between theory and experiment is not an inconvenience to be ignored. It is a door. In this case, it opened directly out of the quantum vacuum. What produces the correction? The electron is not isolated from the fields around it. It is coupled to the electromagnetic field, and through that coupling, the vacuum contributes subtle modifications to the electron's observable behaviour. In quantum field theory, the electron can emit and reabsorb virtual photons. Those photons can briefly participate in further virtual processes. The electron, in other words, is never just a bare mathematical entity moving untouched through an inert background. Its measured properties are addressed by the field activity surrounding it. This is the right place for a visual anchor. Imagine trying to see a single firefly through a faint glowing mist that it itself helps stir. The firefly is still there, still identifiable, but it is never perfectly divorced from the halo of activity around it. That image is only an analogy, and it should not be pushed too far, but it captures the essential correction. The measured electron is not a naked point stripped of all quantum interaction. It is an excitation inseparable from the surrounding vacuum structure. Julian Schwinger calculated the first correction to the electron's magnetic moment in the late 1940s. The answer was simple in form and astonishing in consequence. It matched experiment beautifully. Later calculations added more and more refined contributions. Higher order processes, more loops, more subtle vacuum effects. Contributions not only from virtual photons and electron-positron processes, but from heavier particles as well. As the calculations improved and the experiments improved, the agreement became extraordinary. This is one of the strongest intellectual achievements in science. The theory and the measurement agree to a level of precision that is almost absurd by ordinary standards. The anomalous magnetic moment of the electron is not merely well predicted. It is predicted with a numerical accuracy so fine that almost no other area of science offers a serious comparison. This matters because the agreement depends on quantum field theory, including vacuum effects correctly. Remove those vacuum contributions and the prediction fails, and keep them, and the world matches the mathematics with breathtaking fidelity. This is the decisive point. The vacuum is not a decorative addition to the story of the electron. It is part of why the electron's measured magnetic properties are what they are. There is a subtle limit worth stating here. Physicists often describe these corrections using Feynman diagrams with loops where an electron emits and reabsorbs a virtual photon, or where a photon briefly gives rise to a virtual pair before the process closes again. These diagrams are powerful and predictive, but they are not literal time-lapse photographs of hidden microscopic events unfolding exactly as drawn in ordinary space and time. They are terms in a quantum calculation. Their physical significance is real, but the temptation to over-literalize the picture should be resisted. This is another place where the mathematics is more precise than casual visualization. Even so, the lesson stands without ambiguity. The background changes the particle. Empty space as defined by quantum field theory contributes to the electron's observable identity, and the electron is not the only case. Similar precision reasoning appears elsewhere in particle physics, though not always with the same degree of experimental cleanliness. The broader pattern is clear. Whenever a field excitation is measured carefully enough, it carries traces of its couplings. And because those couplings remain active even in the vacuum state, no particle is ever fully detached from the ground state of the world around it. This destroys a final refuge of the old picture. One might have conceded that the vacuum affects large systems or special laboratory setups while still imagining particles themselves as intrinsically self-contained. The anomalous magnetic moment closes that escape route. The particle's own measurable properties reflect the quantum vacuum, not just its motion through space, not just how it interacts with apparatus, its very observed behavior as a particle. There is also a deeper conceptual reward here. The success of these predictions tells us that quantum field theory is not merely a clever interpretation layered on top of older physics. It is not a change in vocabulary. It is a better account of what exists. If particles were fundamental little objects moving through truly empty space, it would be difficult to understand why a field-based formalism that treats them as excitations embedded in an active vacuum should achieve this level of success. The precision is itself evidence for the ontology. The mathematics works because it tracks something real. Still, we should remain honest about scope. This triumph does not mean the whole story of the vacuum is finished. Quantum field theory is spectacular within its domain, but major puzzles remain. It does not yet provide a complete quantum theory of gravity. It leaves open profound questions about the total energy of the vacuum and its role in cosmology. The right attitude is not triumphalism, it is disciplined wonder. We know enough to say that empty space is physically active. We do not yet know everything about what that activity ultimately means. But one fact is now impossible to evade. The vacuum does not merely sit beneath the world as a neutral absence. It enters the world's measurable details with astonishing precision. It helps determine forces, shifts, atoms, triggers emission, and even corrects the magnetic character of the electron itself. So the question that follows is larger than particle physics. If the vacuum carries real structure and real energy, then what does gravity make of it? What should the universe as a whole do in response to that energy? That is where the story turns from precision triumph to one of the greatest unresolved tensions in modern science. So far, the vacuum has behaved like a triumph for modern physics. It explains why empty space is not truly empty. It helps predict atomic shifts. It contributes to measurable forces. It even enters one of the most precise calculations in all of science. At this stage, you might expect the story to feel nearly complete. Instead, it opens into one of the largest unresolved problems in fundamental physics. Because the moment the vacuum is allowed to have energy, gravity enters the room. And when gravity enters, the numbers stop behaving. This is the hinge between success and crisis. In general, relativity energy is not a passive bookkeeping quantity. Energy gravitates. It curves space-time. It helps determine how the universe expands, bends, and evolves. That principle is not optional. It is built into the structure of Einstein's theory. Mass contributes to gravity. Radiation contributes to gravity. Pressure contributes to gravity. So if the vacuum has real energy and quantum field theory insists that it does, then the vacuum should also contribute gravitationally. Empty space should not just sit there. Its energy should help shape the cosmos. That expectation is not a loose philosophical guess. It follows from combining two theories that each work remarkably well in their own domains. Quantum field theory says the vacuum carries zero-point structure. General relativity says energy affects space-time. Put those two claims together, and the result seems unavoidable. The vacuum should have gravitational consequences, and it does, but not in the way the simplest reasoning predicts. Observations of the large-scale universe show that cosmic expansion is accelerating. Distant galaxies are not merely moving apart because of the initial impulse of the early universe. The expansion itself is speeding up. The cleanest way to describe this within the current standard cosmological model is to say that empty space carries an effective energy density with repulsive gravitational behavior on cosmic scales. This is often called dark energy. In Einstein's language, it can be associated with a cosmological constant. That fact is already astonishing. The vacuum does not merely influence atoms and microscopic processes, it seems to matter for the fate of the universe. But then comes the problem. If you try to estimate the vacuum energy by summing the zero-point contributions of quantum fields in the most straightforward way, the answer comes out absurdly large. Not a little too large. Not wrong by a factor of 10 or 1,000, catastrophically large. The predicted vacuum energy density is bigger than the observed one by an amount so extreme that it has become infamous. The mismatch is often described as the worst prediction in physics if one interprets the naive calculation literally. This is the cosmological constant problem. It's difficult to overstate how severe the tension is. On the one hand, quantum field theory strongly suggests that vacuum structure is real and physically consequential. On the other hand, if the vacuum energy from those fields gravitated in the simplest imaginable way, the universe should look nothing like the one we see. Cosmic expansion would be wildly different. Galaxies might never have formed in the familiar way. Stable large-scale structure would be in jeopardy. The gentle-looking darkness between galaxies would on paper carry an energy burden so vast that the whole cosmic story would be rewritten. That contrast is one of the sharpest in science. The same conceptual framework that gives exquisite precision in particle physics seems to collide with cosmology when its vacuum energy is read naively into gravity. A visual anchor helps here. Picture a vast dark gulf between galaxy clusters. To the eye, it looks like the most inactive region imaginable. Sparse, cold, almost empty. But when quantum theory assigns vacuum energy to that darkness, the calculation balloons into something that, if taken at face value, would dominate the dynamics of the universe. The quietest looking region in existence becomes mathematically the loudest gravitational ingredient. That is not just counterintuitive. It is destabilizing. This is also where honesty about limits becomes essential. Physicists do not yet have a final answer. We know the naive estimate cannot be the whole story. We know the observed cosmic acceleration points to some small but non-zero, effective vacuum-like energy. We do not know why the huge quantum contributions do not appear gravitationally in the simple way one would expect. Something is missing in our understanding. There are several broad families of ideas, but none has achieved universal acceptance. One possibility is that some symmetry or cancellation mechanism suppresses most of the vacuum energy. Supersymmetry, for example, can produce partial cancellations between different kinds of fields. In simplified settings, bosonic and fermionic contributions can offset one another. But in the real world, if supersymmetry exists at all, it must be broken, because we do not observe superpartners in the way an exact symmetry would suggest. That leaves the cancellation incomplete and the problem unsolved. Another possibility is that the issue cannot be resolved inside ordinary quantum field theory, plus classical gravity. Perhaps a true quantum theory of gravity changes the accounting fundamentally. Perhaps vacuum energy is being interpreted too naively, because space-time itself is not yet being treated at the correct quantum level. This is plausible but still speculative. We do not yet have a confirmed theory of quantum gravity capable of settling the matter. A third path is anthropic reasoning. In a multiverse-like picture, different regions may realize different effective vacuum energies. Complex structures and observers would only arise in regions where that energy is small enough not to destroy galaxy formation too early. This line of thought is controversial. It may explain why we observe a hospitable value, but many physicists regard it as incomplete because it risks replacing mechanism with selection, without telling us why the landscape exists in the first place. So the crisis remains, and that crisis teaches something important. The vacuum is not just another detail in the standard model. It is one of the places where our best theories seem to meet and then fail to fit cleanly together. On small scales, vacuum effects are experimentally secure. On cosmic scales, vacuum energy appears to matter, but the bridge between those facts is fractured. That fracture is not embarrassment alone. It is a clue. It suggests that the vacuum may be one of the best places to look for the next layer of physics. Notice how different this is from the early parts of the story. At first, the task was to show that emptiness is not truly empty. Now the task is harder. We must admit that even after learning that lesson, we still do not fully understand what the energy of emptiness means for the universe as a whole. Scientific honesty requires both claims at once. The vacuum is real. Its consequences are real. Our understanding is incomplete. The incompleteness does not weaken the story, it deepens it. Because once the vacuum is allowed to shape not only atoms and particles, but the expansion of the universe itself, the question becomes even more profound. Empty space is not merely where the drama happens. It may help determine the cosmic stage, the cosmic pacing, and perhaps the cosmic ending. The apparent void between galaxies may be one of the dominant ingredients in the fate of everything. And still, there is one more layer beneath even that. The vacuum is not just fluctuating. It may also come with a built-in background value from a particular field that never drops to zero at all. That field changes the masses of particles, helps determine the structure of a matter, and may even carry a hidden warning about the long-term stability of the universe. That is where the story of an empty space turns from active to indispensable. Up to this point, the vacuum has already become far richer than common sense allows. It contains fields. Those fields fluctuate in their ground state. Their activity shifts atoms, modifies particles, and seems to matter for the expansion of the universe itself. But there is another layer that makes the vacuum even less like a mere absence. Some fields do not simply fluctuate around zero and stop there. One field, central to the structure of modern particle physics, has a vacuum state whose value is not zero at all. Even in the quietest possible empty space, it remains switched on everywhere. This is the Higgs field. To understand why that matters, we need a clean definition. The Higgs field is a quantum field that permeates all of space and whose non-zero vacuum value helps generate the masses of fundamental particles through their interactions with it. That is the formal statement. The intuitive version is simpler. Empty space is not just active. It carries a built-in background condition, and that condition changes what particles can be. This is a correction to one of the strongest intuitions people carry from everyday life. Mass feels intrinsic. A rock is heavy because it simply has heaviness. An electron has mass because that is one of its basic labels. But in the standard model, at least for the masses of fundamental particles like electrons and quarks, the story is deeper. Their masses are tied to how strongly they interact with the Higgs field. The field is not something they occasionally pass through. It is already present everywhere. The vacuum itself is part of why particles have the inertial properties they do. That is a remarkable reversal. Imagine the universe before this field settled into its current state. In the very early cosmos, at extremely high temperatures, the Higgs field did not sit at the same non-zero value it carries now. Under those conditions, the symmetry of the electroweak theory was unbroken. The world was physically different. As the universe expanded and cooled, the Higgs field underwent a transition and settled into the vacuum configuration that now fills all of space. From that point onward, particles interacting with it acquired the mass terms that shape the entire architecture of ordinary matter. This is not a decorative detail in the history of the universe. It is one of the reasons atoms can exist in the form they do. An electron without mass would not behave like the electron that helps build chemistry. The weak force carriers would not behave the way they do. The distinction between electromagnetism and the weak interaction would not take the familiar form. Stable structures would be radically altered. In that sense, the vacuum is not merely where matter resides. The vacuum helps determine what kinds of matter can exist at all. The visual anchor here is powerful precisely because it is so difficult to see. Picture the room around you right now. Air, light, walls, your own body. Then subtract all the visible contents in the imagination. Keep going until no ordinary object remains. Even then, the Higgs field, according to our best current theory, would still possess a non-zero background value at every point in that the region. The emptiest possible space would still be carrying a silent field condition that helps make mass possible. This is one of the clearest examples of how modern physics forces a new notion of emptiness. The vacuum is not a blank sheet waiting for laws to act on it from the outside. The vacuum is itself one of the law-bearing conditions of the world. The Higgs boson discovered at the Large Hadron Collider in 2012 matters in this story because it was the long-sought excitation of the Higgs field. That distinction is crucial. The field is the underlying reality spread through space. The boson is a ripple in that field produced under high-energy conditions. This parallels the broader logic of quantum field theory. The field is primary, the particle is the excitation. Detecting the Higgs boson was not merely adding one more particle to a list. It was confirming that this background field required by the theory is physically real. There is also a limit here that must be stated clearly. The Higgs mechanism explains how particles in the standard model acquire mass through their coupling to the Higgs field. But it does not explain all mass in the everyday macroscopic sense by itself. Most of the mass of protons and neutrons, and therefore most of the visible mass of ordinary matter, comes not directly from the bare masses of the quarks inside them, but from the energy of strong interactions that bind those quarks together. So the disciplined statement is this: the Higgs field is essential to the mass structure of fundamental particles, and that structure is in turn essential to the existence of atoms and stable matter. It is not the whole story of mass, but it is a central one. And then the story darkens. Once the vacuum is understood as a field configuration rather than mere absence, a new question becomes unavoidable. Is the vacuum state we inhabit truly the lowest possible one? Or is it only a locally stable state good enough for now, but not ultimately final? In some analyses based on measured particle masses, especially the Higgs boson and the top quark, our current vacuum may be metastable. That word needs a careful definition. A metastable state is one that can persist for a very long time, while not being the absolute lowest energy state available. It is like a ball resting in a shallow valley that is stable against small disturbances, but not the deepest valley in the landscape. If the vacuum of our universe is metastable, then in principle there could exist a lower energy state of the fields. A transition to that deeper state would not be a local inconvenience. It would be a wholesale rewriting of physical laws experienced inside the affected region. Particle masses could change, couplings could change, atomic structure could fail, chemistry stars and ordinary matter might no longer survive in recognizable form. This scenario is often called vacuum decay. It should be handled with great care. It is a theoretical possibility, not an observed threat. Current estimates suggest that if our vacuum is metastable, its lifetime is immensely longer than the present age of the universe. So this is not a practical doomsday forecast, but it is conceptually revealing. It means the vacuum is not only active and necessary, it may also be precarious in a very deep sense. The laws we live under may depend on the universe residing in a particular field configuration that did not have to be the only one. That possibility changes the philosophical weight of empty space once again. The vacuum is not merely where events happen. It helps decide what an event can be. It determines which particles exist, what masses they carry, and what structures can endure. If the vacuum changed, the rulebook would change with it. So by now the phrase empty space has become almost unrecognizable compared with its ordinary meaning. Empty space fluctuates. Empty space exerts influence. Empty space contains a non-zero Higgs background. Empty space may even encode the stability conditions of the universe itself. And that leaves us with the final step. If fields are fundamental, if the vacuum is structured, and if matter itself is just organized excitation on top of that structure, then the most basic question is no longer what objects fill the universe. The deeper question is what kind of process the universe is. That is where everything we have built so far must finally come together. After all of this, the strangest part of the story may be the simplest to state. The universe does not appear at its deepest confirmed level to be built from things in the ordinary sense. It appears to be built from fields, not fields as metaphors, not fields as temporary calculation tools. Fields as the enduring physical entities that fill space, support excitations, transmit interactions, and define what the vacuum even is. Once that becomes the working picture matter light, force and emptiness all change meaning at once. This is the final reversal. For most of human thought, reality was imagined as a collection of objects occupying space. Stone, stars, bodies, air, water, atoms. Even when science refined the objects, the grammar remained familiar. Smaller pieces replaced larger pieces, but the world still seemed to be made of pieces. Space in that picture was mostly the gap between them. It was the container. Physics then consisted of learning how the pieces move, collide, combine, and separate. Quantum field theory inverts that grammar. Space is not a mere container if fields fill it everywhere. Matter is not primary if particles are excitations of those fields. Emptiness is not the subtraction of being if the vacuum is the ground state of a structured physical system. The universe begins to look less like a warehouse of objects and more like a continuously present set of underlying fields whose excitations produce everything we ever observe. That does not make tables, mountains, or bodies unreal. It makes them emergent in a deeper way. A chair is real, your hand is real, a neutron star is real, but each is real as an organized pattern built from field excitations and held together by field interactions. The solidity of the chair is not a primitive fact. It is an outcome. The stability of atoms, the rigidity of matter, the spectrum of light, the chemistry of life, all of it depends on the properties of fields and on the vacuum state those fields occupy. That is a major cognitive reward because it clarifies a question that often remains blurry in popular discussions. Modern physics does not say the visible world is an illusion. It says the visible world is not fundamental in the way it seems. The deeper layer is not made of ordinary little objects. It is made of field structure, quantum states, and lawful patterns of excitation. The ordinary world remains real, but its reality is relational and emergent rather than primitive. There is also a profound continuity hidden here. The electron field in your body is not a private local ingredient belonging only to you. It is the same electron field that exists everywhere else. The electromagnetic field carrying signals through your nervous system is the same electromagnetic field through which starlight crossed interstellar space before reaching your eye. The Higgs field that contributes to the mass structure of matter in your cells is the same field filling the space between galaxies. The universe is not made of disconnected local copies of a thing. It is made of shared fields with local excitations. This is one reason identical particles are identical. It is also one reason the old boundary between you and the rest of the cosmos becomes less absolute at the deepest descriptive level. That does not erase practical boundaries. Your body is still your body. A star is still a star. But the ontological separation is less severe than common sense suggests. Different objects are not made from fundamentally different private substances. They are different stable arrangements in the same underlying field-based reality. A useful visual anchor is the night sky. You stand on a dark hillside and look upward. A star shines. Between you and that star stretches an immense darkness that seems empty. But after everything we have traced, the scene no longer divides cleanly into object, observer, and void. The star is a complex set of field excitations. The light travelling to you is excitation of the electromagnetic field. The darkness between is not nothing but the vacuum state of many overlapping quantum fields. Your own retina, brain, and body are also organised field excitations. The scene is not objects separated by absence. It is one field-filled universe expressing itself in different regimes. This is where the philosophical temptation becomes strong, and it should be handled with discipline. Physics does not by itself tell us the final metaphysical meaning of this picture. It does not prove grand spiritual conclusions. It does not erase all mystery, and it does not solve every open problem. Gravity still resists full quantization. Dark matter remains unidentified. The cosmological constant problem remains unresolved. The interpretation of quantum theory is still debated. It would be dishonest to pretend the map is complete, but incompleteness should not be confused with vagueness. Some parts of this picture are extremely well established. Quantum fields are not speculative in the loose sense. They are the framework behind the Standard Model, one of the most successful theories ever tested. Vacuum effects are not poetic language. They are measured in laboratories. The Higgs field is not a metaphoric convenience. Its excitation has been detected. The uncertainty lies not in whether empty space is physically rich, but in how far the implications ultimately go and how they connect to the remaining unfinished parts of fundamental physics. That distinction matters because it protects wonder from exaggeration. The truth stated carefully is already more than enough. Empty space is not an inert void. The vacuum is not the absence of physics. It is one of the places where physics is most concentrated. It stores the ground state of the fields from which particles arise. It constrains what can exist. It modifies matter even when no real particles are present. It may influence the expansion of the universe. And through the Higgs field, it helps determine the mass structure of the world we inhabit. So the original question returns in transformed form. What is a quantum field? It is not a little object, it is not a conventional medium. It is an underlying physical entity defined throughout space, capable of existing in different quantum states, capable of being excited into what we call particles, and capable of retaining irreducible structure even in its lowest energy condition. And why is empty space not empty? Because when particles are absent, the fields remain. When excitations are absent, the vacuum state remains. And when the vacuum state remains, so do fluctuations, background values, interactions, and the physical possibility of everything else. There is a final scale shift hidden in that answer. We often speak as if reality is built upward from matter into stars, life thought and civilization. But in this story, the deepest flaw is not hard substance. It is a structured quantum background from which substance itself emerges. The nothing beneath things is not nothing. It is the precondition for things. The quietest state of the universe is not a blank zero. It is the baseline of a generative system. That is why this topic changes how you see the world once it settles in. The gap between atoms no longer looks like useless space. The darkness between galaxies no longer looks like mere absence. Silence no longer means nothing is there. The vacuum becomes one of the most consequential realities in physics. Not because it contains ordinary hidden stuff, but because it is the field-filled ground from which ordinary stuff can arise. And once you see that the universe looks different, less like a collection of isolated objects drifting in emptiness, more like a single continuous physical tapestry whose calmest regions are still full of law structure and latent possibility. The void did not turn out to be empty. It turned out to be the deepest layer we had been mistaking for empty all along.